Kia ora koutou, nau mai, haere mai. Welcome to lesson 1 for introductory physics. So this is the start of the actual course content, the physics content, not just how we're going to run the course. What we're going to look at today is what science is and what physics is. Those of you that have already studied other sciences probably know the first few slides worth of material talking about science in general. Regardless, please do continue watching as we then start to talk about physics and also the intersection between physics and mathematics. So as usual, we'll jump over and we'll watch the slideshow, which I will narrate as we go through. And I'll jump back to this screen a few times, this camera a few times, and just talk a bit. There's going to be quite a lot of talking, just me sort of riffing a little bit during this first lesson. It is only 19 slides. Hopefully it will be fairly short, but I do sometimes get a bit carried away. All right, here we go. Lesson 1, science and physics. What is science? To start with, we're going to talk about science. We're also going to bring in language a little bit, something a lot of people don't think is too relevant with science, but I'll talk about that a bit as well. So what's science? Science is a very broad term. It actually means a number of different things. It can mean the system we use for understanding the world around us, with the scientific method at its core. But it can also mean the body of knowledge that we form through that research and investigation. So science can be the knowledge that we have gained through scientific investigation. Science can also be an attitude. It's more of a scientific attitude rather than calling it science specifically, but it's a way of thinking about the world. It's an idea of curiosity and wanting to understand what's going on. Scientific methods vary slightly depending on where you look, but in general they will look something like this. You start by observing something, you form a hypothesis about that thing or process, you design an experiment and predict the outcome based on your hypothesis, then you carry out the experiment and thus gather data. You then analyze the results. You look at that data and say, what does this mean? And you either support or falsify your hypothesis. So that is the scientific method. Look around the world, form an idea about how it works, make a prediction about how to work in a certain circumstance, observe that certain circumstance, and then use that to update your idea about the world. Notice that on the previous slide it said a scientific method. I already mentioned they vary slightly depending on where you look. That is because the scientific method is not a prescription of how to do science. It's not saying if you want to do science you have to do this, step 1, step 2, step 3. It's not saying that. What it's saying is that people in general, when they were investigating the world, did follow these relatively similar steps all the time. That's just how people did science. And so when they got together and sort of agreed, all right, let's write this down, let's make it a bit of a list, it was a description, not a prescription. So the difference there, if you're not familiar with the terms, you're probably familiar with the term descriptive, but prescriptive is saying how you should do something. It's it's beforehand, saying how you should do it when you go to do it. Descriptive is just describing it, it's saying what did happen. So scientific method is descriptive, not prescriptive, but it will generally always follow that same process. Now, as I've just defined a couple of words, it's a good segue into language in science. So language is complicated. What words and sentences mean varies greatly depending on context. There's a whole branch of philosophy where we talk about language and the words and word games and what context it's in and so on. And for us studying science, it's a very real issue, and it's one we have to be constantly aware of, even though a lot of people tend to sort of ignore it or just assume everyone understands. The biggest issues are when we have words that mean something in everyday language and mean something different in a scientific sense. There are words that mean very similar things in everyday language and scientific senses, and that's fine if they mean the same thing. There's not usually a lot of confusion, but sometimes they have quite different meanings. To illustrate this, we're going to talk about a few words that we've already met, or we've sort of segued into. We didn't actually state the word fact, but we're going to start with fact. When you observe something, that observation is a fact. So fact is generally pretty much the same in everyday life and science. A fact is a thing that is undisputed. If you observe a ball fall down when you drop it, It is a fact that the ball fell down when you dropped it. If there are other people around that also observed this ball fall down, they would agree on the fact. So generally, facts are not debated. Generally, facts are the things that everyone can agree did happen. The hypothesis is the testable idea about how the world works. So once you've observed the fact, you use all the facts that you have, all the information you know about the world, and you use that to form an idea about how the world works. And that's what we call a hypothesis. So our hypothesis might be that when you drop something, gravity causes it to accelerate downwards. That might be our hypothesis, and that is a fair one given that's what's actually happening. But usually they're created based on facts. Sometimes they're created on information that's conveyed to us from someone else. So it might be a fact that I'm telling you things accelerate downwards due to gravity. That's a fact that I told you that, but you would then need to, I'm not sure why I didn't even touch my mouse, and that just went to the next slide, but apologies. So it might be a fact that I told you, but it's not a fact that it does fall downwards, right? The fact that I told you. So there's this distinction between information and the hypothesis. And also, hypotheses must be falsifiable. The whole point of a hypothesis is it's something we can test. If we can't test it, then it's no use. It's not a hypothesis, and it's not following the scientific method. It's not a scientific endeavor. Laws and principles are hypotheses which have been repeatedly tested and never falsified. So these are words that do get used in everyday language, but slightly differently. So a law in everyday language is generally talking about a legal system. A law is a rule of society, and it's one that you are supposed to obey, but you don't have to. There's nothing physically stopping you from speeding, from going past 100 kilometers an hour on the open road, but you are supposed to limit yourself to 100 kilometers an hour because that is the law. In science, a law is something that just is true. Right? So a law is just a true statement. They are technically hypotheses. They have not been falsified so far. We've done lots of experiment, lots of scientific investigation. We've never falsified them. Laws are hypotheses that have been tested so much throughout the history of science that we pretty much agree, okay, they have to be true. They have to be the case. Right? They're still not a fact. They are a law, not a fact. A fact is the observations. The observations were used to test the hypothesis and to build up our confidence in that hypothesis to the point where we said, okay, this is a law because it just always seems to be true, but it is still not a fact. The fact is that it's been observed and has agreed with the law over and over again. And theories are a collection of facts and well-tested hypotheses. Now, this is one of those words. This is the one I've been building up to. Theory in everyday language and in science is very, very different. So we'll talk about that now. Is it a theory? Theory is one of the worst offenders for miscommunication when we're talking about science with people who have not studied science, as you will gather from the idea of people saying, oh, evolution is just a theory, things like that. So it's a big point of contention. And the problem is that in everyday language, theory just means some random idea you've come up with. Someone can walk up to you and say, I've got a theory that my neighbor's a serial killer. That is true or not. That theory is not a theory in the scientific sense. It doesn't mean it's not a theory. It's a theory in the everyday casual language sense, but it's not a theory in the scientific sense. In science, a theory is something that we are so confident that it's true, and we've tested it so many times that we can't even imagine it not being true. That's what a theory is. So when we talk about the theory of evolution, right, it is a fact that things evolve. We know that things evolve. We have bones. We have a visual representation of evolution. It's a fact that things do evolve. The theory of evolution is the explanation for why they evolve. And that has been tested against observation for so many times, for so long, through all of our scientific history since Charles Darwin. And it's always been shown to be the case. So that's why we call it a theory. That's science in general. We're now going to talk about physics specifically. So physics specifically is the fundamental science. That doesn't mean it's the best science or the easiest or the hardest or the most important. It's just the fundamental one. It's the one that's right down at the very basic building block level of the universe. It deals with the fundamental interactions between energy and matter. And I said right down at the building block of the universe scale, so right down at atoms and all their components, but it's also right up through to stars and galaxies and the entire universe. So it's talking about interaction, and it's talking about energy and matter. The other sciences overlap with physics a lot, or physics with them. There are points where we'll border on chemistry and we'll border on biology and things, and I'll often point those out and say, right, we're going to stop here, because if we go any further, we're looking into chemistry, or we're looking into biology, or we're getting into pure math, or whatever the case may be. But it's still important to think of physics as sort of being that underlying one. For example, we can talk about atoms and what they're made of and how they form molecules and how those molecules interact with each other. But once we start getting into the bonding between those different molecules, we're now talking about the chemistry of those different bonds, and we start getting off into chemistry. Learning physics. Physics is often thought of as scary or too difficult. There are 3 common reasons. This is anecdotal. This is through my experience teaching physics and talking to students of physics. There are 3 common reasons. One is that people tend to have this perception of it being only for geniuses. 2 is that it's very stepwise, and if you miss a step, or you fail to understand one lesson or 1 year, or you have a poor teacher 1 year, it's going to make it very difficult to pick up the next lesson that builds on top of that. And finally, physics is often confused with mathematics, and this is something I'm going to talk about a lot more in the last few slides of this lecture. The good news is you absolutely can learn physics. There are definitely some geniuses who come along and make amazing breakthroughs in physics, but they are very few and far between. The majority of physicists do not make those big breakthroughs. The majority of people studying physics just do the hard work, do the repetition, do the exercises, figure out what's going on, and put a lot of time and effort in it. And that's how you can learn physics. You do not need to be a natural genius. If you are a natural genius and you understand physics innately, then you may well make the next breakthrough, but you certainly do not need to understand physics. A common step, a common missing, sorry, I've completely screwed up that sentence. A common problem with learning physics is the idea of missing a step. If you learn something and then the next lesson builds on top of that something, but you didn't actually grasp that fully, it's going to be very difficult to understand that next lesson. So that stepwise nature makes physics very easy to fail, very easy to fall over. Similar to maths, although maths is a little bit more obvious in its stepwise process. Physics is very similar in that sense. You do need to get a grasp of all the lessons, and that's why I keep reiterating, please work through all 36 lessons in order. I'm going to start assuming you know physics. I do assume you know some maths, as I said, but I assume you know physics, and I'm going to build you up, hopefully, so that you understand everything along the way. That's also why, as I keep saying, please ask questions. If you are struggling with a concept, don't leave it till later to try and figure it out. Try and figure it out now and ask questions if you're not sure. Because if you fail to understand one concept, then the next time we need to build on top of that, it's going to be that much more difficult for you to build on it. And as promised, the last section of this lesson is talking about physics and mathematics. So physics and mathematics, what's going on here? Maths is a tool. We need it in order to analyze some physics problems and get numerical answers. But the problem is usually on the side of the teachers, not the students. And that is the lack of distinction between physics and maths. The teachers don't specify when they're doing physics and when they're doing maths. In fact, what they often do is they jump straight to the maths. They ignore all the physics and they just start writing maths down. They do it in their head. They never show you the physics. So that's no problem on the part of the students. That's entirely a problem on the part of the teachers. The issue, actually before we do this, I'm going to jump over and go to the document camera, and I've prepared a little problem, and I'm just going to solve this. I don't expect you to understand this. It is beyond anything that we've talked about yet, because we haven't actually covered any real physics. But I am just going to solve this the way that a lot of teachers would, just to demonstrate what I'm talking about. So here's a problem. We have a box with a mass of 1 kilogram, and we have a ramp at an angle of 30 degrees to the horizontal. The flat side, the horizontal length of this triangle, this ramp, is 10 meters. And we want to know how long will this box take to fall? If it starts here at time t equals 0, then when is it here at the bottom? That's our question. And what I'm going to do is solve it the way, as I said, a lot of teachers, even university lecturers, would solve it on the board for students. They would say, all right, here's our box, it's at an angle of 30 degrees. So therefore, our acceleration down the slope is going to be given by acceleration is equal to g sine theta, which is 9.8 times the sine of 30 degrees. And that is equal to 4.9 meters per second per second. As I said, you don't know acceleration, or you may know it, but I haven't taught you it yet. The idea is just to follow along. You can hopefully follow all of this maths. You should know the maths. The acceleration down the slope is 4.9 meters per second. We now need to know how long the slope is. How far is the box traveling? I'm going to call that delta x. And given this is just a right-angled triangle, 30 degrees here, 10 meters here, we can figure out the length of that hypotenuse. That is just going to be 10 over the cosine of 30 degrees, which is 11.55 meters. So the box is accelerating at 4.9 meters per second, is traveling 11.55 meters. Therefore, we can use kinematic equations. This is part of one of our lessons. Again, don't worry about it now, just follow the math. Delta x equals a half a t squared. That means that t is equal to the square root of 2 delta x over a. That's just rearranging that equation. And that means that our time is going to be equal to the square root of 2 times 11.55 over 4.9, which is equal to 2.17 seconds, or 2.2 seconds, rounded to two significant figures. And so hopefully you followed all of that math. And if you followed that math, then that proves my point that you can think you are following along what the teacher has said. But I did not tell you any physics. I didn't say any physics at all while I did that. Right? There is some that I implied because I used equations that were relevant to the physics, but I didn't tell you any physics. And if you could follow all of that working, then it leads you to this false impression that you can solve this physics problem. But just based on that, that's just maths. If you are basing it entirely on that, then you have no way of knowing you can actually solve the physics problem, because all you've done is solve the maths problem. And that is, as I said, that is the problem. We have students that follow along with the maths. And if I give you a really similar question, if I change the angle, change the length, then ask you the same question, you can probably solve it just by following those same steps, but you're never doing the physics, you're just doing the maths. What that means is that if I give you a question which is now slightly different, but using similar physics, you don't even know where to start, because all you've done is learn the maths. And if you don't understand why you don't understand it, that's a big problem, because you don't know where to look to solve that, to fill the gap in your knowledge. So if you think you understand the physics, and then you get a problem where you can't understand it and you can't solve it, then you're not sure why. That becomes a really big mental block in terms of your progress. So hopefully what this demonstrates, and what I really want you to grasp, is that you can easily follow along the maths, and you can understand the maths, and you can even solve similar problems using that same maths. But if you don't understand the physics, if you don't understand where those numbers came from and why we had to use them in the way we did, which is what I'm going to be teaching you throughout the first lessons. I don't expect you to know it now. But if you don't actually understand the physics before we get to the maths, then that's going to be a big problem a little bit further down the line. So the solution is just to be very aware of that distinction. Realize where the physics stops and where the math starts. And that's something I will continuously do throughout the lecture videos. I will always try and point out, okay, at this point, we've done the physics, we've thought about the system. Again, I'll define all these terms soon. We've thought about it, we've figured it out, now we can move on to the maths. I'll always try and make that distinction. I apologize in advance if I forget to on any occasion, but I will try and remember. But I also want you to practice doing that. When you're doing physics problems, even really simple ones, even ones where you think, oh, I don't even need to worry about the physics, I'll just go straight to the maths. Please do the physics. Consciously think about the physics. Even if you don't write it down, consciously think about it. Then once you've got everything ready to do the maths, switch over to the maths and make sure you tell yourself, I've done the physics, now I'm doing the maths. And that way, when you get to a problem that you can't solve, you can stop and think, is this still the physics that I'm not sure about? Or have I done the physics and I'm just stuck on the maths? Because then you know where to look to try and resolve that problem. So that's the end of this first lesson. There's not really a lot of content in terms of things you can go away and test and learn. There is a problem sheet with just a couple of questions about the scientific method, but there's no real questions yet about physics or physics maths boundary, but hopefully it's set you up ready to start tackling that content when we do.